All right, hello everybody. Welcome back. This is lesson 1.7.9. We're going to be looking further at functions on the graph. And throughout this lesson, we are going to be looking at how we can use equations, data tables, or graphs to answer exponential questions. So equations, data tables, and graphs are all tools that you can use. Desmos being the graphing calculator that we are using. This is also the graphing calculator that you use on your 11th grade SBAC tests. So it's good for you to get practice using Desmos calculator. Like always, please join through joinpd.com. Our code today is WXOBA. If you come in late, it'll be right above me here, okay, so that you can still join into the lesson. All right, so moving on. So we're going to be interpreting exponential functions. We'll be representing them using equations, tables, and graphs. Okay, so here's our warm-up. So Lynn and Diego are discussing two exponential expressions, x squared and 2 to the power of x. Lynn says, I think the two expressions are equivalent. Diego says, I think the two expressions are only equal for some values of x. Do you agree with either of them? Explain or show your reasoning. Okay, so this is a discussion question, so you'll be able to type. Here's a data table to kind of help you kind of get thinking about who is right or wrong. So you would type in the discussion, Lynn, I think Lynn's right because, or I think Diego is correct because. And the question is x squared equal to 2 to the power of x? Are these two equal expressions? So our main question are these equal? So I'm going to now show some responses. Okay, so here's a couple responses from our students. So one student says Diego is correct because some values collide as represented on graph 2. Uh, so let's take a look at this data table here. So it seems like we know that these aren't equal, but let's see a clear way to explain why these aren't equal. So x squared is the same as 1 times 1 because our x value is 1 here. So then 2 to the power of x would be 2 to the power of 1. Okay, so that makes this value 1 and this one 2. Already from the beginning, these are not equal. So then are they sometimes equal? Well, if we look at 2, 2 squared is 2 times 2. Okay, 3 squared is 3 times 3. Okay, 4 squared is 4 times 4. 5 squared is 5 times 5. 10 squared is 10 times 10. Okay, but then 2 to the power of x, which is not x squared, I'm always going to have a 2 here, but it's telling me how many 2's there are. So this one has 1 2. This one has 2 2's, so 2 to the power of 2. This one is 2 to the power of 3. This has 3 2's. Okay, this one has 4 2's. This has 5 2's. And then this one has 10 2's, which I'm not going to write all of them because that's too many. Too many 2's. All right. So, so if we're looking at this, clearly 1 squared is not the same as 2 to the power of 1, because this is equal to 1 and this is 2. However, 2 squared is the same as 2 to the power of 2. Okay, so we can see here that they are the same. So, and then here, 3 times 3 is 9. This is 2 3's. Here at 4, 4 times 4 is 16. And we can see that 2 times 2 is 4, 2 times 2 is 4. So actually at here, it is also going to be the same. So for some values, depending on what our x is, for example, if our x is 2 or if our x is 4, x squared and 2 to the power of x are going to be the same. Okay, however, they're not always going to be the same. These are two different expressions. So, it's important to note that x squared is not the same as 2 to the power of x. Okay, so the number that's our base and the number that is our exponent matters. Okay, even though sometimes they will be the same, it's not always going to be the case. Okay, so one student here, a good way to prove something logically is to show just one counter example. So Diego is correct because x to the power of 2 is 1 and 2 to the power of x is 2. So how you would correct this, how you would make this explanation better, you would say that 1 squared equals 1 and 2 to the power of 1 equals 2. Therefore, x squared does not equal 2 to the power of x. Because x squared is not always 1, as we can see here. 2 to the power of x is not always going to be 2. However, 1 squared equals 1 and 2 to the power of 1 equals 2. Therefore, these two are not the same. Okay, so moving on, we're going to take a look at another problem. So we're going to look at the cost of solar cells. So the cost in dollars to produce 1 watt of solar energy is a function of the number of years. Okay, so last time when we were discussing functions of, like last lesson, if this is a function of years, that means the years is going to be our horizontal axis, and that the money, the dollars, is going to be our vertical, because the dollars is a function of years. Okay, and the number of years since 1977. So this is our starting point. So when t is 0, it's going to start at 1997. So from 1997, which is 0, to 1987, which is here at the 10 mark, 10 years later, it could be modeled by an exponential function f. Okay, and here once again, as I said briefly in the last lesson, we're going to start seeing a lot of functions represented as f. So even though our output is dollars, even though that's our vertical axis, instead of saying dollars using d variable, a lot of times they're going to be using f. This is one of the most common notations to represent a function. Okay. So so you should be able to draw on the slide. So what is the statement f of 9 equals 6 saying about the situation? So what does this mean in English, in words? What does f of 9 equals 6 mean? So in the context of this situation, what does this mean? Okay, and then again, what about f of 4? What about f of 3.5? Do these values mean anything in this context of the problem? All right, so I'm going to show just a few responses. So one student says that 9 is the input and 6 is the output. That is absolutely true. So that would be true for every situation. We know that the input, which is the value on the bottom, okay, so 9 is input. We do know that. This is going to be our input, which is also our independent variable, and that 6 is our independent variable. But how about this context? What about this? What about in this particular context? Okay, because that's always going to be true. However, like when it's asking what does it say about the situation, we really want to talk about what does it mean in the context of this solar energy and the cost to produce solar energy. All right, so I see that another student here says that 9 years after 1997, the cost per watt is $6. Okay, so um, what this means in the situation, we know that this is the time after number of years since 1997. Okay, so this represents 9 years after 1977, sorry. So 9 years after 1977, the cost of watts is going to be $6. So the cost of watts, which is the unit for electricity, okay, we measure length in inches, centimeters, and yards. We measure water as like liters or gallons. We measure energy or electricity in watts. Okay, this is our unit for electricity, for energy. So the cost of watts is going to be this $6 here. Okay, so that's what this means in the context of our situation. Okay, so then what about the next one? Okay, so this is the same thing. Okay, the input tells us the amount of years after. So our input that is inside this f, inside our function f, is going to tell us the years after 1977. So if this is our function f, okay, inside this is going to be the years after 1977. Okay, so any input, any number inside of our function, so it's a function of years, a function of time, this is going to be the amount of years after 1977. So then if the number inside is the amount of years after 1997, the outside is going to be the cost of the watts. So this is going to equal our cost of watts. So this is the cost of 1 watt. So 1 watt of energy is going to change as the years go on. Okay, and this kind of makes sense because as the years go on, making solar energy is going to be cheaper and cheaper because our technology is going to get better and better. Okay, so the number on the outside will be the cost. The number on the inside is the number of years out after, because this is always going to be our output. Okay, because we have dollars is a function of time, and then this is going to be considered our input or our independent variable. Okay. So knowing this, what about when f of t equals 45? So this looks different than what we've seen before. The major difference here is that there's a t inside of our function here. It says f of t instead of giving us a time. So what does this mean? What would t be if f of t equals 45? Okay, what does the t represent in this context? So, kind of back up here, if I was actually to solve for f of 4 and f of 3.5, what we would have to do is substitute it, is we would go to the number, we would find 4, and then we would go up here to see that this is about 25. So f of 4 would equal 25. Likewise, here, if this is f of 3.5, I would go to the 3.5. So if this is 3, this is 3.5. I would go up to my line. I would take a guess, and I would say this is about 30. Okay, so for these problems, if I'm given the number in the inside, I go from the bottom, from the inputs, and I go up to the line, and then I see where that is in the outputs. So then if I'm given f of t equals 45, how would you find what t is? Okay, so I have one student, I see at least one, who has an answer for this. Okay, so I saw them write f of 2 equals 45. Okay, so where did they get this 2 from? Okay, so if you're given the output, what you would do is you would go from the output side of our graph, 45, and then you would go to our find the graph and find the appropriate input, okay? So here, this is 45. So these go up by 5s because it goes 5, 10, 15, 20, 25, 30, 35, 40. So 45 is here, so I would start on this side instead, and then I would go down to my input. Okay? So if I'm given 45, we would find that the input is going to be t equals 2. Okay. So if you're given the input, you would start on the x-axis or the horizontal, you would go up to the line, and then you would find the appropriate output on the vertical axis. Okay. However, if you were given the output, you would start with the vertical axis, the y-axis, go to the line, and then go down to the horizontal. Okay. So when you're using a graph to answer these kind of questions, it's important to really pay attention to what they're asking you for. If they give you the number inside, you're starting on the horizontal and then going to the vertical. However, if you're given the number on the outside, like here, you're going to be starting on the vertical, going to the line, and then down to the horizontal. Okay, so what does T represent? So in this context, you would be looking for when is the cost $45? Okay, you're asking when is the cost going to be $45? Well, it's going to be $45 2 years after 1977. Okay, so then the last question is, by what factor did the cost of the cells change each year? Okay, so looking at this graph, how are they changing each year? Okay, so I see a student who wrote an equation. So they saw that 80 was our starting point, that 80 was how much the cost of the watts began at. So they took the starting point of 80, okay, but then I see them write 2/3 here. Okay, the question is, where did they get this 2/3 from when they were writing their equation? Okay, so on the graph, where they got this 2/3 from is, you see here they have 60 and 80 as 2 points, 2 solid points that are on the line, and they're also next to each other by 1. So here is 1 year apart. It goes from 80 to 60. So that means our factor is going to be 60 divided by 80. Okay? And then if you simplify this fraction, the zeros will cancel out. It'll become 8/6. If you divide the top and bottom by 2, you will get, if you divide the top and bottom by 2, you'll get 3/4. So I'm not sure where the 2/3 came from in that student's equation. Okay, but if I find the actual growth rate, it is going to be 3/4. This is the actual factor, the growth factor. Okay, so that's using the graph to find the growth factor. You could have also, if that was confusing, make a data table. So using the data table, you would say, okay, at 0 it's 80, at 1 it's 60, at 2 it's 40, okay, And then you could try and find the pattern here at 3. Okay, so, but you're going to have to do the same sort of steps. You're still going to have to do 60 divided by 80 to figure out, you're still going to have to do 60 divided by 80 to find the growth factor, which if we simplify, we realize is 3 quarters. Okay, so I see the student has 15 and 20. I'm not really sure where they got the 15 and 20 from, because this point here is by the 60. So the numbers that we should have divided was 60 and 80 to find. But this question wasn't asking us for the equation. It was only asking for the factor. By what factor did the cost of the solar cells change each year? And that factor was 3 over 4. Okay, but writing the equation can help you discover what that growth factor is. And also note that this is decreasing, and the fraction that we got is less than 1, which is how exponentials decrease. Okay. So we're going to take another look at a different problem. All right. So this is going to be about a piece of paper that is folding. So thickness T in milliliters of a folded sheet of paper after it is folded n times is given by the equation T equals 0.05 times 2 to the power of n. What does the number 0.05 represent in this equation? And how many folds would it take before the folded sheet of paper is more than 1 millimeter thick? How many folds would it take before it is more than 1 centimeter thick? Explain how you know. Okay, so for this problem, a piece of paper is getting folded, and the thickness of the paper is going to increase with the number of folds. Okay, so the question is that what if we're folding a piece of paper and it's getting thicker as we fold it, what is that initial value supposed to represent? What is that 0.05? Okay, so we have a piece of paper, and when you fold it, the paper is going to be thicker than it was before, right? The height here is going to be more. If you fold it again, once again, the thickness is going to double. So as you keep folding, your paper is eventually going to be very thick. Okay? It's like this is no longer going to be the thickness of a piece of paper, right? The more you go. All right. So if we compare that to original piece of paper, the thickness is going to be, see, this is very thin piece of paper, but when I folded it multiple times, it's going to be a lot thicker than it was before. Okay, this has a very, very large width, This thin piece of paper does not. So the question is, what does this 0.5 represent in this equation? Okay, so I'm going to show some student responses because I want to see your words for it, how you guys describe it. Okay, so one student said that 0.5 is the starting, and that is true. This is always going to be the start. Okay, so this is the starting, but the starting what? So we know that 0.5 is the start. Is the starting what? The start value of thickness of the paper. So 0.05 is the starting thickness of the paper. So combining two of your responses there will make the we will make the answer here. So 0.05 is the starting thickness of the paper. So 0.05 milliliters is how thick the paper is in the beginning. It's very, very thin. Okay. So then so we know that this is the starting, and we also see that the thickness is going to double because this is 0.05 milliliters. This is 0.5 milliliters. So if I fold it on top of each other, it's going to double because now I have two of those widths getting stacked on top of each other. So if I fold again, it's doubling again. Because once again, now I have two of the thicknesses stacking on top of each other. Okay, so this is doubling in thickness as you continue to fold the paper. Okay, so then the question is, how many folds would it take? So I'm curious how you'd solve this. There is a graph here. There's an equation. You could also make a data table to solve this question. So there are three ways to solve this question. I'm interested in how you solve it. But the question is asking, how many folds does it take before the sheet of paper is more than 1 millimeter thick? And remember that this is calculated in millimeters. Okay, so how long will it take before it's 1 milliliter thick? Okay, and this is important to think like, okay, which of these, they did not label these axes for us, right? So a data table is one method to solve it. You could use the graph, okay? The equation would be most difficult to use because we have not learned logarithms yet, but you will in integrated math 2 and 3. So also think what kind of function is this? Like blank is a function of blank because the second one here would be our units for our horizontal. The function would be our units for our vertical. Okay, so n would be the number of folds, or this would be our x, okay? When you start with 0 folds, it's going to be 0.05 milliliters thick, okay? After another fold, okay, it's going to be, you're going to double that. So you would do 2 times 0.05 to get 0.1. Okay. Then after 2 folds, this would double again. 3 folds, it would double again. Okay, and you could keep going. Okay, until you find when it's going to be more than 1 milliliter thick. So this will double again. Sorry, that was not right. I know what 4 times 2 is. And this would double again. Now it's 1.16. Okay. So using the data table method, okay, you would find, if you started at our starting value, you would find that it becomes more than 1 milliliter thick after 5, okay? So after 5, so it would take 5 folds for the paper to be more than 1 milliliter thick. Okay, so it would take 5 folds for the piece of paper to be more than 1 milliliter thick. Now, if you wanted to use the graph, you would go here and you say, okay, I want to know when it's 1 milliliter thick, how many folds will it take? So if you go to the graph, you'll see that it'll land somewhere in between 4 and 5. Now, the number of folds have to be a whole number. Okay? And because of that, a better way to represent this graph would be with dots, because our number of folds have to be whole numbers. I cannot fold my my paper more than I cannot fold it a fraction of a fold. That doesn't make any sense. I either fold it, I do 1 fold, or it's not folded, right? This is still a little open. So it's either folded or it's not. Okay? So when I go here to find the 1 milliliter, I go down, I see it's in between 4 and 5. So you would have to round up, and the answer would be 5 folds. Okay? So using the data table, you would go down and you would see when this is more than 1. Using the graph, you would start at the 1 and then go down. Now the second question asks for 1 centimeter. So centimeters, you have to know, there are 10 milliliters in 1 centimeter. There's 100 centimeters in 1 meter, right? So there's 1,000 centimeters in 1 meter. So getting here to 1 centimeter would be the same thing as getting up to 10 milliliters. Okay? So to answer the second part of the question, you could go all the way up to the 10, and you could say, okay, how many folds is it going to take for it to be more than 10 milliliters? Okay? More than 1 centimeter thick. So you go here, okay? You go down and you see, okay, it has to be in between 7 and 8. So that means it would take 8 folds for the paper to be 10 centimeters thick. Or sorry, 10 milliliters thick, which is the same as 1 centimeter. Okay, if you wanted to use the data table, instead of the graph version going from the output to the input, which is number of folds, you would keep going down and keep multiplying until you get to 10. Okay, now, so if you're given a graph, it is a little faster sometimes to use the graph, but it's a little bit more exact using the data table. You're a little bit more confident that you find an actual number instead of eyeballing something like you would for a graph. But know that graphing and using a data table are both great ways to find the answer to these kind of questions. Okay? All right. So, here's another problem for you to practice that is somewhat similar. Okay? So, instead of the thickness of the paper, so we're still folding papers for this problem. However, instead of thickness, we're talking about area. Okay? So, let's say the area of a sheet of paper is 93.5 square inches. Okay, so this whole thing is 93.5 square inches. Now, when you fold it, that area is going to half. This is now half amount of the area as it was. Okay? If you fold it in half again, it's going to be another half of the area that it once was. Okay? So every time you fold it, the area, the space, the rectangle is going to have a smaller amount of area. So, something you need to do for this problem then is like, could you write an equation that represents this situation? And also, can you find the area if you folded it in half once, twice, and 3 times? So we know the starting area is 93.5 inches. What would the area of our paper be if you folded it in half once? What would that area be? How could you find that? And then if you fold it in half twice, what would the area of that be, this paper be now? And again, if you fold it in half thrice, 3 times, what would the area of this paper be? If you're having a hard time organizing the answers to problem 1, a great way to organize the answers would be a data table, where you could have your x and then your f of x here for your area. Okay. So I see a student using, I like the equation they used. I see them, they used A for area, and then F for folds, equals the starting area, which is 93.5. They weren't sure what the rate was, but then they said to the power of the number of folds. Okay, so let's help this student here. What would the rate be for this equation? Okay, so I know the area is my output, and area is a function of folds. Okay, so my starting area is 93.5. How much is it going to change by depending on the number of folds? Okay, so think about it. If this is my area, 93, and I fold it in half, what's this new area going to be? How would I find half of 93.5? Okay. So if my start is 93.5 and I fold it once, what is half of 93.5? How do you find half of something in math? If I had 8, what's half of 8? Okay, I've seen one student say 46.25. Let's see if that is really half of 93.5. So if I had my paper, 93.5 square inches, I fold it in half. My new area is going to be half of 93.5, which is indeed 46.75. Okay. So then so now my area of my paper is 46.75. If I fold it in half again, what's my new area? Okay, so I'm seeing something in the 23s. So let's try it. 46.75 divided by 2 is going to be 23.375. What is the pattern here? What is this problem decreasing by? What would the factor be in here? What's the growth factor? What is it changing by? What is the area changing by as I fold? And then we'll divide it by 2 again. Because now that my area is 23.375, if I fold it again in half, what's the new area going to be? Okay, you get 11.6875. Okay, so what is it changing by? What factor belongs in here? My starting value was given to me as a number right here. So then what's my rate of change? What's this changing by as I fold this paper? What's the area changing by as I fold the piece of paper? Okay. 0.5. Yes, half. This is changing by half. As I'm folding the paper in half, so the area is changing by half. Okay? So you could either say this is 1 over 2, 1 half, or you could say it's 0.5, which are the same thing. Okay? So this is my equation for the situation. Okay? So the key thing here was the word half. This is what told us about what our rate was going to be. Okay? This half here lets us know that our area is changing by 1/2 each time. It's decreasing. Okay? So now, taking a look at it, our next question in this context, can n take negative values? What is n? N represents the number of times it's been folded. Okay, so they wanted us to use n for our equation. So sure thing, the variable doesn't matter. I'll change that for my problem so it makes it feel better. So if n represents the number of folds, can n take negative values? What would a negative fold look like? So if when n is 0, that means I didn't fold the paper. How would I negative fold this paper? You can't. That doesn't make sense. There would be no negative folds in this context of the problem, right? So the answer is no. You can't have negative folds in this context of the problem. So negative n's does not make sense. So the number of folds cannot be smaller than at the start of 0. so to change this phrasing here, it would have to be smaller because the values cannot be negative. So folds cannot be smaller than 0 because I either didn't fold the paper at all, or there's one fold or two folds, but I can't have negative folds. That doesn't make any sense. All right. So the next question, what about A? Can A take negative values? What does A represent? A represents the area. Can this area of this paper ever be negative? Okay. So can this paper have negative area? Well, no. Okay. Area is space that exists in our world. Okay, so there's either no area, there's no paper, or there is area, there is some paper, but it's never going to be negative. Okay. So, no. Okay, so first of all, it starts off positive and it's never going to reach under 0 because exponentials cannot go under a certain part. So, yes, in real life you can only fold the paper so far, but also area can never be negative. Okay? So, I like that this student here said that in real life paper can only fold so far, which is true. So that would never get to the below 0. And also area is always positive. So it could never be negative. And once again, this is a situation where the graph is, it's better to represent this graph as as points. The reason being is that folds are only whole numbers. So I either folded it 0 times, 1 time, 2 times, 3 times, 4 times, 5, 6, 7, 8, and so on. Okay. And then it would stop because there's only a certain amount of times you can fold a piece of paper before it becomes impossible, right? So here's 1, 2, 3, 4, 5, 6, and 7 is pretty much you can't do it. Okay, so this graph in real life would be best represented by these points here, 1, 2, 3, 4, 5, 6, 6, because 6 is about how much you can fold a paper in real life. Okay. All right. So this discussion question afterwards. So someone says, so how many folds does it take before the folded paper is more than 1 millimeter thick? Someone said it takes 1.5 folds because I looked on the graph to check the points. What do you think about this response? Identify the error and critique and write an improved explanation. So I'm going to really quickly go back. I'm going to take a shot of this graph here, so we'll have it. Okay. So here's the graph. The question is, how many folds does it take before the folded sheet of paper is more than 1 milliliter thick? And the person said that it's going to take 4.5 folds. Like, why is this person incorrect? Okay, so one person says that 4.5 does not make it more than 1 milliliter. It makes it exactly 1 milliliter. Okay. One person says the reason would be better with an example or proof or disproof. So we came up with the answer to this problem. Our correct answer is 5 folds. Why is the answer 5 folds and not 4.5? What's wrong with this student's answer? Here we go. Excellent, because you cannot fold half paper. Yes. Okay. The reason that this student is incorrect, it's not that their logic was bad for finding the answer. You can use a graph to find the answer. That is perfectly fine. The issue here is we cannot have 4.5s of a fold. Folds have to be whole numbers. Okay, excellent work. So, yes, so it just does not make sense. They want to know, when is the paper going to have a thickness that is more than 1 milliliter? So after 1, 2, 3, 4 folds, it's not enough. 4 folds is not enough. There is no thickness of the entire paper in between the 4th fold and the 5th fold. It's either going to be the 5th fold is more than a millimeter, or the 4th fold is more than a milliliter. Okay, so the reason this student is incorrect is because you cannot fold the half paper. Like, you either folded it fully or you did not. Okay, so it's important to understand the context of the problem, because even though if you go to the graph and you see that 4.5 is going to be a little bit more than 1 milliliter, you cannot have, this is not a reasonable answer. This is not in the domain. Okay, so the reason we learn a domain is because we need to know what's possible as an answer. This is not possible in the real world. You cannot do 4.5 of a fold. You either have, it's either folded or it's not. Okay, so it has to be not an exact number, but a whole number, because all numbers are exact. Okay, whole number means a non-decimal number. All right. So here is another another lesson synthesis question to see if we understand. Okay, so in this lesson we used exponential functions to answer questions about different situations. In a previous lesson, we saw a function f defined by f of t equals 240 times 1/3 to the power of t, represents the area of algae in square yards after t weeks of treatment. Discuss how this function could be used to find the area of algae 6 weeks after the treatment, find out how when the algae would drop below 10 square yards. Okay. So these are asking us for two different things. Okay. So good. I'm seeing a student say, okay, if we were trying to find the area, you would have to substitute. So because area is our output, right? So if area is our output, that means that we would have to use substitution. We would have to plug in. Okay? So this student here said plug in 6 for t. Okay? So if I have 240 times 1/3 of to the power of t, which here is 6, and then in our calculator, our graphing calculator, we can put 240 times 1/3, close it off, use our caret on our keyboard to make it to the power of 6. Okay? So this would be the area of our algae after 6 weeks. Okay, and our area is in yards squared. Okay? So if we were trying to find the area, you would have to plug in if we were looking for the output. So if you're trying to find the output, area is a function of time, you would have to use plugging in. But what if instead you wanted to find when? What if our goal was to find when? How would we answer this kind of question? What if we wanted to find when would the algae drop below 10 square yards? How do we answer these when? So if we wanted to find the area, that's easy. We just plug in 6 for t. But what if we wanted to find out when would the algae get to a certain area? Okay, so okay, excellent. So I'm seeing a student say, well, you would have to plug in 10 for f of t or a graph. Okay? Now, plugging it in for 10 is something that we don't know how to solve. So if I put 10 equals 240 times 1/3 to the power of t, we do not know how to solve this until integrated 2. So this is going to be something that you look how to solve using algebra in IM2. Okay? So for IM1 purposes, we are just, if you're looking for when, if you're looking for the input, when you're given the output, if you're looking for input, you're going to have to use the graph. Okay, so and how we use a graph to find the output when we're given, so find the input when we're given an output, so we go to 10. Okay, so we're like, all right, this is 50. This is going to be 25. It's going to be somewhere around here. Okay, so it's going to be somewhere around 3. And to find it exactly on a graph, so using our graphing calculator, okay, if I graph my equation, 240 times 1/3 to the power of x. Okay, So I want to know what's x going to be when y equals 10. Okay? So here what I did is I graphed my exponential, which is the purple curve, and I want to know what's x going to be when y equals 10. So now I just have to click the intersection point here. My exact answer is going to be 2.893. Okay? So when the algae is 10, okay, by writing the line, by using the line y equals 10, and then using my graphing calculator to find the intersection point of my line and my graph, okay, I find that my answer, it's going to be 2.8 weeks. However, okay, so we could say this is weeks. And whenever we're talking about time, it does make sense to have part of a week be done. Okay, so we could figure out which day it could be. 2.8 is near the end, so maybe 2 weeks and then Friday. Okay, so this would be exactly when. You could say for sure after the third week if you wanted to keep your units in weeks. For sure after 3 weeks and exactly at the 2.893 week mark. Okay. So if you're given a graphing calculator, if I wanted to find when, so you can graph your equation and then you can put y equals 10, okay, and then find the intersection point and it'll tell you exactly when, what input you're looking for, the x value you're looking for. Keep in mind that we will not be doing logarithm method, but if you wanted to see that out of curiosity, you would take, you would first divide that to the other side. 10 divided by 240, and then you would find the logarithm of that. But again, the logarithm method is something that is not going to be used until integrated 2 or 3. So just keep that in mind. And it's very hard to type it in the calculator. Okay, it wants us to use decimals. But keep that in mind. So if you wanted to use the logarithm method, you would take the rate of change down here, and then you would do what you're looking for divided by the starting value to get the exact number here using logarithms. Okay, so you'll see that you'll also get 2.8927. However, using the logarithm method is something that you'll be doing in IM2 and IM3 and later maths. All right, so then we'll take a look quickly at the cooldown. All right, so this is bacteria in a petri dish. Okay, since an antibiotic is introduced, what is the appropriate value of f of 4.5? Approximately, what is d when f of d equals 4,000? Explain how you would use your graphing technology to use f of 15. All right. So best thing to do here, you could make an equation. Okay, so we know that our starting value is going to be 1 million. Okay, so if our starting value is 1 million, okay, we know f of t equals 1 million. Okay, to find our rate of change, you would take the 900,000 and you would divide that by your 1 million to find your rate of change. Okay. You can cancel out all these zeros that are the same, and you could get 9 over 10, which is 0.9. So this would be our rate of change to the power of t. So if you wanted to approximate f of 4.5, you could now put this in our equation. 1 million, I need another 0, times 0.9 to the power of 4.5. Okay, so the amount of bacteria, so the reason it's an approximation is because you cannot have a portion of bacteria. So a good approximation for the first one would be 622,432 bacteria. Okay, so this, because it's a person or bacteria, I'm just going to round up. Okay. And then now that you have an equation, we can actually approximate our output. Okay. Because when we're given the input, all you have to do is substitution. Okay, into t. But when we're given the output, using our graph, okay, if I graph this in my Desmos calculator, graphing calculator, I can find the exact answer. So if I do 1 million times 0.9, so sorry, y equals 1 million times 9 to the power of x, okay, I will get my graph. Okay, and then I would do, I want to approximate when y equals 400,000. Okay, so if I zoom out enough, and you can see that this is very difficult to look at, so I'll make my x-axis a lot smaller, maybe from 0 to 10. Okay. I can find the exact amount of time that passes to get to 400 million. Again, you just do y equals the number the output you're trying to find. You graph your equation, and then you find the intersection point. So this is going to be 8.697. And this is the best method we have for estimating these values until you get to IM2 where you can actually use logarithms, which is the best way to solve these kind of exponential problems. So this is about how many days. Okay, there'll be a part of the day that goes by as possible. Okay, so 8.697 days. Okay. And how we could use our graphing calculator to see the 15 mark. f of 15 is here. Okay. So if you wanted to find, you could use the same method, but see here how they give us the 15 on the inside? They give us our input. So this is when x is 15. You could graph when x is equal to 15. And then if you didn't want to substitute, you could find the intersection point here to find that when x is 15, the amount of bacteria in the population is going to be 205,891. Okay, it would be the population of bacteria. Okay, so whether they give you the y, you can still use this method, just put y equals for the graph. If they give you the x, you can use the x equals method to find the x value that where it intersects with the graph. All right. So that's how you could use the graphing calculator method to find the x, or if they give you the y value, if they give you the output, you can use the graphing calculator to find the y. Okay, so that's it for this lesson. I hope you go to the tutoring if you need help, and I'll see you next time.